All right. This is the review session. Basically what we're going to do is test one from February 25th of 2016, the spring test for Physics 214. Standard boilerplate info. This version is, let me see if I can find it. I think it's the first one in the file. Trying to think what I end up figuring out. I want to say it's maybe the voltage of the battery. So it's either 100 or maybe this, just 58. So this is version 58. Because I know that for this one, see how I hand wrote it in? What I was doing is I was changing the values of the capacitors, and that was the number I was changing for the appetizer. So there we go. Real quick. 1 ampere equals 1 coulomb per second. Negative particle moves from left to right. It slows down. So the acceleration is that way. What is the direction of the electric field? Left to right. Acceleration for a negative particle is always opposite of the electric field. You rub silk on a glass rod, which is false. I've slowly been eliminating these dumb answers. Is the glass rod positive? Yes. Some charge is transferred? Yes. Electrons move from the rod to the silk? Yes. Protons move from the silk to the glass? No. Answer D. 2 resistors are in series. 90 degrees is the dumb answer. In series, which of the following is true? Now, if they're in series, those currents don't add up to be the equivalent current. They are the equivalent current, so it has to be C. The potential difference across a capacitor doubles the electric field between the plates. Dumb answer. What does it do? Quadruple, triple, decreases, or doubles? Doubles. And the equation that you would use is V equals ED. The potential at ground is always 0. In Brevard, you let go of a particle that has a mass of 3 grams. It sits there, it moves nowhere. In which direction is the electric field? Floor to ceiling. The ground is attached to a negative lead of a 15-volt battery. So you've got battery, ground is attached to the negative lead. What is the potential of the positive lead? Positive 15 volts. Unit for charge is what? Coulomb. These two, this one we won't know yet. That one's dumb. What are the units of Newton? Or what's Newton units for? Force. What uses the units of joule? Energy. You charge an electroscope by induction. What actually touches the electroscope? Your finger. The potential difference across a resistor is 0. Which of the following is true? No current flows through the resistor. Current is defined as potential difference divided by resistance. If the potential difference across the resistor is 0, the current must be 0. You have 2 resistors in parallel. The current flowing across 1 doubles. The resistors remain constant in their resistance. What is the current? What happens to the current across R2? It increases. Let me show you why. If this increases, that means that the potential difference across that capacitor, or I'm sorry, across the resistor increases. If that potential difference increases, that potential difference increases as well because it's the same potential difference. Therefore, the current across this must increase as well. Two capacitors in series, value of C1 doubles, C2 does not. The equivalent capacitance does what? It increases. Remember in both, we did both both examples on the Tuesday lecture. In both cases, I even worked out the math on the series one because I wasn't sure. In both cases, if you double C1, the equivalent capacitance increases for both, in series or in parallel. Parallel, it's easy to figure it out since they just add up. Two resistors are in parallel. Which of the following is true? I think this is a repeat from an earlier. The currents, oh, I'm sorry, no, it's not. B, they add up to be the equivalent current. Which of the following can only be positive? The electric field. Acceleration, left or right, negative, positive. Velocity, ooh, this one's capitalized, that one's not. They can both be positive or negative. Potential, all can be positive or negative, that leaves only electric field. I will say this, problems like that will not be in the multiple choice. Oh, I'm so mean. The basic conversions you guys know, so I'm not going to give you free points. Positive particle moves from left, excuse me? Positive particle moves from left to right. It accelerates. What's the direction of the electric field? Once again, I'm getting deja vu. So the electric field must be from left to right as well. Which of the following is not true? Potential is a vector. Potential is always a scalar. Now really what I don't like the wording of this. I should say velocity can be a vector, force can be a vector, which it is. Electric field can be a vector. Potential can be a vector. No, it can't. Potential is always a scalar. You charge the electroscope by conduction. What touches the electroscope? C, the rod. The object is doing nothing. Which equation best describes this? Cricket, cricket. E, sum of the forces is equal to 0. It has to be either A or E because these things oppose each other. One, it is equal to 0. One, it doesn't equal to 0. If it's doing nothing, then the sum of the forces is equal to 0. You rub rabbit fur on an ebonite rod, which is now true? It's negative. The ground is attached to the positive lead of a 15-volt battery. So now, it's like that. What is the potential at the negative lead? Negative 15. Because that has to be 0. When you step through there, you go down 15 volts. So that is negative 15. 4 meters at 90, you guys aren't gonna, I mean, you're gonna get the answer. but 4 meters at 90 is that C. Thank you. But it's not, the vector addition stuff I've pulled out of the multiple choice. Which of the following can be positive or negative? Potential. Current is plotted on a graph as a function of potential difference. The slope of the graph is what? A, inverse of resistance. All right, and that is the multiple choice. I haven't exactly written the test, but the multiple choice has been cleaned up. E. All right, now for the problems. Looking at this stuff, there's only so many, I mean, there are general fields of problems that I can do. The appetizer problem can be an equivalent resistance, could be kind of a simpler RC circuit problem. This is a metaphysical certainty. You're gonna have to add up E fields. This is a metaphysical certainty. You're gonna have to add up resistances and figure out equivalent circuits and stuff like that. Those two are guaranteed. The numbers won't be exact, but there's nothing else I can really do. First appetizer. Given this, equivalent capacitance is 58 microfarads. What is the value of H? So it's a squoosh type problem. First you want to write it out, and then you write out all the steps. Ooh, I'm doing all these weird angles. Ooh, everybody should be scared. No, the reason why I do all these weird angles is to make you familiar with it, so you go, that ain't frightening me. I'm gonna change it. Okay. So what I've done is I've bent the wires so it looks like more of a conventional circuit. The first squoosh is going to go for there and there, which will leave me with three capacitors in parallel. Then I do the second squoosh. And then I do the third squoosh, will give me the CEQ, which is 58 microfarads. The 58 microfarads is a bizarre number. Why did I pick 58? Maybe I planned ahead. What you need to do is you need to start doing the equivalent capacitance and slowly work down. H and 3H, they're in series, so I'll call this C1. So C1 is the inverse of H added to the inverse of 3H inverted. This makes this 3 over 3H, so this is 4 over 3H inverted, which means that this upper C1 is 3H over 4. The bottom, the lower, I'm going to call it C2. C2, 1 over 2H plus 1 over 5H. The common denominator is 10, so this makes it 5 plus 2, or 7 over 10H inverted, or 10H over 7. So now we have three capacitors, C1, an H, and a C2. This makes it C3 is C1 plus H plus C2, which is 3H over 4 plus H plus 10H over 7. Common denominator of 28. So 21H plus 28H plus 40H over 28 gives me 4989 H over 28. That is C3. C3 is in series with a 2H capacitor. So this is 1 over 2H plus 28 over 89H. Not sure if I was being nice or cruel to the class, but CEQ is 1 over 2H plus 28 over 89H. Oh my goodness, I must have been angry at my students. Common factor of 89 times 2. So this is 89 over 178H plus 56 over 178H inverted. Please let me do the math correctly. So it is 178H over 145. And that is C equivalent. So C equivalent is actually 58 microfarads. So 58 is equal to 178H over 145. So H, let me see if I had the spreadsheet running on this. 145 times 58 divided by 178 is, oh, I was being mean, 47.2 microfarads. And that was the answer. I may have looked at this and just went heck with it, just throw in numbers and let everybody else sort it out. I will say this, when I write the problems and I'll figure it out, one of the things I will say is, are the problems running nice, are the numbers running nice, or are they running evil? For stuff like this, you're gonna expect something evil. I'm gonna have, because this is just darn near difficult to fix. This, I'm gonna try. I'm gonna see if I can get that straightened out. But all it is just an equivalent capacitance circuit. Yes. It is in a series, but remember, series capacitors add like parallel resistors. Yes. Series capacitors, like there's a chart that I drew for the class. I'll draw it again. You have resistors, capacitors, series, parallel. Resistor series, you just add. For parallel resistors, you take the sum of the inversions and then invert it again. For parallel capacitors, you sum them up. For series capacitors, you sum up the inverted numbers and then invert it again. So you can just look at this and see the pattern between the two. For the vector addition problem, first things first, draw this thing out. The point that I want to study is at -2, -2. So that's the point, and I want to know the E field at that point. I'm going to have two charges, one at -2, +5. This is a -2 microcoulomb charge. The -2 microcoulomb charge is awesomely placed because it is directly above the point that you're studying. So the negative produces an E field that is at 90 degrees, a pure Y vector. One of the charges will be either to the left, right, above, or below, but not at a weird angle. One of them definitely will be something like this. The other charge location is at 4, 0. It is a +3 microcoulomb. It's positive, so it radiates outward, so I'm gonna need that line in just a bit. Its E field looks like that. And really what I'm starting to do is I'm starting to draw a little mini origin at the point where I'm studying. Because it's a negative charge. The E fields, excuse me? One of them's probably going to be positive and the other one's going to be negative. And as to which one will be in a nice position, I can't tell you that. Now the first one, the negative charge, what you need to do for each of these is first find the magnitude of that E field. E is K Q1 over R squared. Now really this should be big Q1 because this is the magnitude. This is 9 times 10 to the 9th, 2 times 10 to the -6, all divided by its distance squared. Its distance is 1, 2, 3, 4, 5, 6, 7 millimeters, or 0.007 meters squared. So this becomes 18 times 10 to the 3 divided by 0.007 squared. 3.67 times 10 to the 8th newtons per coulomb. That is the E field of this. And when you're looking at, let's just say, what is the E field as a vector? That E field from the negative charge is going to be 0x hat plus 3.67 times 10 to the 8th Y hat newtons per coulomb. I'm getting everything lined up to be in component notation. Now when you look at this right here, I've kind of drawn a little mini origin, and this is the reference angle that I'm looking for. But I still need to do the same thing that we did up here. I need to find the magnitude of the E field. So once again, E is K Q2 over R squared. The R is the distance from there to there, and you can write this out as a right triangle. This is the delta X, or 2 millimeters. This is the delta Y. This is the delta x, or 1, 2, 3, 4, 5, 6 millimeters. And the same distance is here at 2, which will be used in just a minute. So r squared is equal to 0.006 squared plus 0.002 squared. I don't need to square root it because I'm going to square it back anyway, so I just write it like this. This becomes 9 times 10 to the 9th, 3 times 10 to the negative 6, all divided by 0.006 squared plus 0.002 squared. 6.75 times 10 to the 8th newtons per coulomb. That's the magnitude of the vector. Now this one is not as easy as the first vector. The first vector is instant conversion. This one requires a little bit of how do I figure out theta r. The reason why I put the 2 over here is when you look at it, this is a parallel line, that is a parallel line. I need to know what that angle is. That angle is the equivalent to that angle right there. That reference angle you can get by the inverse tan of y over x, inverse tan of 2 over 6. The units don't matter because they cancel out anyway. Inverse tan of 2 divided by 6. And I get 18.43. Excellent. I finally got it into a situation where I can start dealing with it in a normal vector addition way. The reference angle is 18.43 degrees. The x component is that e from the positive times cosine of theta r. My y is e sine theta r. I'm now breaking down the vector. A 6.75 times 10 to the 8th newtons per coulomb at a third quadrant reference angle of 18.43. How do I know it's a third quadrant? Because the arrow was drawn in a quadrant 3 direction.
So it goes off where the arrow is drawn?
Pointing, not where it is. Remember that with a vector, and this is an important lesson, scalars are magnitude. Vectors are magnitude and direction. Notice in neither case, position was mentioned. Position was never mentioned. Vectors only care about where they're pointed, not where they are. I know, hold on. I know my hand is in the way. Oh, it scrolled down. Hold on. Okay. Let me back this up as well. So what's that x value? 6.404 times 10 to the 8th x hat. What's the y component? Okay. Now what I did is I didn't include the signs just yet, because what I want to do is the 18.43, when you multiply it by 6.75 times 10 to the 8th, you will get all positive numbers. When you're doing vector addition, you type in only positive numbers, you only get positive numbers back. it's because it's a third quadrant, we use our logic to apply the negative signs in there. We've broken our vectors. We're now ready to add. Adding the vectors means that our total E field vector as a component vector is negative 6.404 x hat plus 1.54 y hat. And what I'm going to do with this is, and this is something that you can do, is you can put the powers on the outside times 10 to the 8th newtons per coulomb. And that is the resultant vector in component notation. Now that we're done with that, let's do the final bit, a recombination. The hardest part was setting it up and then breaking down the vectors. Once you've broken down the vectors, you are good to go. Steps 2 and 3 should be fairly quick. The total E field magnitude is 6.404 squared plus 1.54 squared. Once I get a value for that, I'm going to tack on the 10 to the 8th. So I get 6.59 times 10 to the 8th newtons per coulomb. Negative x, positive y. It's a second quadrant angle. X, y, the close reference angle. Y, x, e. We've just determined the magnitude. The reference angle for this is inverse tan of y over x. So inverse tan of y, 1.54 divided by 6.404. They both end in 10 to the 8th. It's unnecessary to write it because they just cancel. And you get this. 13.5 degrees. Now in the previous class we were doing a vector addition problem, and at this point I just smacked down 6.59 times 10 to the 8th at 13.5. That's wrong. Why? Because it's a second quadrant angle and this is just a reference angle. So how do I get the absolute angle from this reference angle for a second quadrant vector? You subtract it from subtract it from 180. So this becomes 180 minus 13.5, or 166.5 degrees. Excuse me? I said that this vector here was a third quadrant, but the sum, the resultant, is a second quadrant. And excuse me? Okay. Let me first write down the answer so I can feel better about myself. 6.59 times 10 to the 8th newtons per coulomb at 166.5 degrees. That's the answer. That's the equilibrium. Now, one of the things that we're going to do is I'm going to answer your question. Remember when he asked the question about something about location and quadrant dependency? Now granted, if you're treating that as the origin, physically, yes, that's the first, second, third, and fourth quadrant. But what we're talking about now is a first, second, third quadrant vector. For a first quadrant vector to be called a first quadrant vector, it has to go up and to the left, or up and to the right. Second quadrant, up and to the left. Third quadrant, down and to the left. fourth quadrant, down and to the right. Notice at no point in those descriptions did I say physically located in quadrant 1 based on the origin. It was all based on where it was headed. This is due up. It's an instant conversion vector. This one is down and to the left. It's a third quadrant vector. I could do the same vector like that, and that is a third quadrant vector. Granted, it is physically located in the first quadrant, but locations, reword, vectors are not location dependent. They are magnitude dependent and direction dependent. They are not location dependent. Now, as to why this is a second quadrant angle, let's do the tail to tip method just to show what it is. That's the first vector, that's the second vector. If you do the tail to tip method, or tip to tail, I don't care how you say it. What you do notice is the point at where you start and where you finish with regard to the E field is up and to the left. It has a positive Y and a negative X. That's a second quadrant vector. It doesn't matter that it's physically located in the third quadrant. Physical location quadrants are different from vector quadrants. So it's a subtle difference, but it's an important one. Yes? I'm only asking for E field. There was no charge at that point. Actually, if I did put in a charge at that point and then asked for the E field at that point, you would just disregard it. It would kind of not even make sense. So if I ask for an E field, it's going to be at a point where there's a vacuum at that point. Okay, problem 2. I could. It could be as simple as you find the E field, you get the magnitude, and I say, okay, now put a 5 microcoulomb charge at that point, what's the force? And all you would do is take the charge and multiply it by the E field. Done. I think what you're asking is for me to make it more complex than what's necessary. I could do that if that's, I mean, it's all about me helping you. And so if that's what you want, I could write that down. No, it's for that particular problem, I'll either add up the E fields or add up the forces, not both.
Yeah, that's awesome.
Yeah. So. All right, for number 2, it's an RC capacitor or RC circuit. Looking at the charges, it starts at an unknown max charge. It is shown that it is an unknown max charge, which means, he's done the math and we don't need it. It then is at 2 coulombs at 10 seconds and 0.4 coulombs at 20, which means this thing is discharging. Yes?
In our notes for discharging and charging RC circuits, we use voltage instead of charge.
Let's talk about that because I knew it was going to come up. And actually I'll tell you this, the problem that I'm leaning towards, if it is an RC circuit, we're sticking with voltage. But let me tell you why these equations aren't that big of a deal. The discharging equation is Vmax e to the negative t over tau. And I'm not going to write the other one because it's the same procedure. What do you know about the relationship between charge, potential difference, and capacitance? Is that the Q is equal to CV, or Q over C is equal to V. So V becomes Q over C, Vm becomes Q max over C. The C's cancel because we're dealing with the same capacitor, and it's Q equals Qm e to the negative t over tau. So that's the setup. It's not a big, there's no big mystery with this. It's just a simple substitution. But the math is, I mean, for either capacitance or for potential difference, it's the same thing. I intentionally was being a jerk to the class and did not give them the maximum charge. I just said, no, I'm not giving it to you. Not gonna do it. So what you do have is Q1 is equal to Q max e to the negative T1 over tau, where tau is RC. I gave you the R, I didn't give you the C. And then what I did is I divided it by Q2, which again is Q max e to the negative T2 over tau. Q max is I need to formalize the wording for this. The three types of numbers that I give you because you do need them, second tier or second form, which is this, numbers that I don't give you because you don't need them. You don't need Q max. Why? Because in the way that we're doing this, they cancel out. It's a lot like the Doppler shift problem. You know the frequency as it's going away, you know the frequency as it's coming towards. You don't know the frequency that it's really making. So what you do is you divide away by towards, and then the source frequency goes away. So Q1 over Q2 becomes e to the negative t over, or T1 over tau, e to the T2 over tau. Exponentials in the denominator, when you lift them up, they lose their negative signs. This becomes Q1 over Q2 e to the T2 minus T1 over, and now what I'm going to do is put the tau in the denominator of the exponential. Because minus T1 over tau plus T2 over tau is T2 minus T1 over tau. I mean, it's... which just becomes that. And then Q1 over Q2 e to the T2 minus T1 over RC. The only unknown in this equation is the value of C. So let's go get it. Natural log of Q1 Q2 is equal to T2 minus T1 over RC. I'm looking for C. So C is equal to T2 minus T1 over R natural log of Q1 over Q2. T2 is 20. T1 is 10. R is 4 times 10 to the 6th natural log of Q1 2 divided by 0.4. And that gives me I get 1.55 microfarads. This may be a math. I don't think. Do we have confirmation on what it could possibly be?
It could be significantly. It is. It's 1.55.
Okay.
My
All right.
calculator is shortened.
Okay. Good. So that's the answer for C. Okay, last problem, the circuit problem. For all circuit problems, regardless of what I'm looking for, find REQ first. Find out what it is, either in equation form or give me a number. That's the first thing you want to do. So first, draw this thing out. Ooh, everything is in weird loops and turns and stuff. But in the end, it's this. The first squooshing is the upper and the lower to make R12, R3, 4, and R5. That's the first squooshing. Second squooshing, you box in those two and you end up with R1, 2, 3, 4, and R5. And then the final squooshing, you get REQ. So really what I'm doing initially is just drawing out the various squooshings to get this. What do we do in the first? We have two sets of series resistors. All you got to do is add them. So R12 is 10 plus 20 or 30. R34 is 30 plus 40 or 70. So that's R12 and R34. The next task, they're in parallel, you squish them together. So R1, 2, 3, 4 is 1 over 30 plus 1 over 70 inverted. Which is 21 ohms. So R1, 2, 3, 4 is 21 ohms. The last one, R5, is 5 ohms, so 21 plus 5, which is equal to 26. That is REQ, that's the first answer. The next step, I naught. I naught by my definition is the current flowing through the battery. So I naught is 100 divided by 26. So 100 divided by 26 is 3.85. I would keep it in a fraction for the moment, and its fraction is 50/13 amps. But when you're boxing answers, the 3.85, I would go with that. It does. I would say that the default, and honestly, to ask that during a test is entirely appropriate. I'm not gonna be weird with the ground. There are those multiple choice questions where you put the ground on the weird side of the battery. But in terms of a test problem, I'm not gonna play games with that. It would affect VA where you put the ground, but the standard, never on a test before have I put the ground anywhere other than there. And I have no intention on changing that anytime soon. So, which means I had, yes? No, go ahead. I would say if it's not drawn there, assume that the ground is the bottom of the battery. Now, one of the things that is an advantage by drawing all this stuff out is you know all of the intermediate resistances. What we really need in order to get VA is that we have to find the potential difference between there and there first. I'm going to call, well, this is just V. And this, I'm going to call VB. And actually, I made it real, I mean, this is incredibly easy. VB, you could either step down from here, or you can step up through R5. The easiest way, the fastest way to get VB here is to step up from R5. How you get VB is simply 0 plus I naught R5. I naught is your initial potential, the potential at the ground. You went against the current across an R5 resistor, which means that the potential change is the current times the resistance, and it has a plus sign in front of it. We were going upstream. I naught 50/13ths and R5 is 5. And this is a horrible equation. 250/13ths, or whatever that is. (19.23 volts). So what's the purpose of understanding VB? Well, if you understand VB, you can now get the current going through R1 and R2. So I'm going to call this I12. I12 is V high minus V low divided by the resistance of 1 and 2. V high is V, V low is VB, the resistance of 1 and 2 is R12, or just the sum. V is 100, VB is 250/13ths, and R12 is 30. And I'm getting horrible, horrible fractions.
How did you know to use R12?
Hold on just a second. 35. So the numbers are getting slightly more clean. Yeah, say that again.
How did you know to use R12?
In this equation, the current is the difference between the potentials divided by the resistance. Here, let's look at R1 and R2. Do I know the resistances? Yes. Well, if I wanted to know the potential there, I could, if I knew what V was. I do. V low in this particular case across R1, I'm looking for. So that's an unknown, that's okay. The resistance I know, but I don't know the current flowing through R1. That's an unknown at the moment. How do I get that current? I study another type of circuit in this problem. I know V high, I just found VB, the V low. To get the current, I divide that difference by the total resistance. And that gives me I12. The advantage of knowing I12, which is the equivalent current flowing through resistors 1 and 2, is that I1 and I2 and I12 are all the same value. Yes, question? I stepped up from 0 across R5 against that current. Use Ohm's law. Effectively use a variant of this. So I naught, the current flowing through R5, is VB minus V low, which is 0, divided by R5. So VB is equal to I naught R5. And that's it for that. There was another question over here that may have been answered. Yes?
So the point VA, the current flowing through would be different if it was on the other side of our signal?
If VA was over here, yeah, it would be different. No, the current, you're asking about the current.
Right.
The current flowing through this wire here is the same as the current flowing through that wire there and there. Once it meets up at this node, that is the sum of that current and that current. We now have I12. We have the current flowing through resistor 1 and resistor 2. To get VA, now I know the resistor value, I know the high value, the low value I'm looking for, the current through R1 is now known. Now I can find VA. Now is the appropriate time to look for it. So V minus VA divided by R1 is equal to I1. I'm looking for VA. So V minus VA is equal to I1 R1. V minus I1 R1 is equal to VA. You may now plug and chug. 100 minus I1 35/13 R1 10 is equal to it's equal to 7307. Or 08, 73 volts. Okay, I'm feeling better about the numbers. And so that's VA. With so many resistors and batteries and currents and stuff like that, to get the numbers to work out right is kind of difficult. It can be done, but it takes time, and my students don't allow me to think. They come by, my wonderful students come by all the time and ask questions. Yes?
Okay. You know how I asked if you would do like the force field on the column? If you would do that,
Yeah.
would you work it the same?
Yeah. The force would be vector addition with the same thing. But instead of using E equals KQ over R squared, you would just use KQ1 Q2 over R squared.
Would the directions be different?
It could be.
Yeah. What the multiple choice
Multiple choice problem
number 2?
2. This one?
Yeah.
Okay. Particle moves from left to right. It's a negative particle. So there's our negative particle. That's the velocity vector. It slows down. Slowing down implies acceleration is opposite to velocity. So to get the acceleration of the negative particle to go backwards, the E field has to go to the right. And that's it. All right, sounds like we're done. Yes. I can't, come on up. If you got questions, come on up.
You said problems 1 and 3, like on the back, would be a certainty.
Yes.
So what about problem 2? Like, what should we expect in place of that? Should we expect?
Could be. Could be a motion problem. Like a charged particle in an E field, that kind of thing.
Okay, I don't understand like on a circuit. So this is Ohm's law. I know that. How do you know the current is going this way? Besides, like, where is I1? That's a better question.
Where's I1? I1 is there.
Okay. Oh, that's an I. Okay. All right. So then I2 would be here.
And I1 and I2 are equal to each other.
So why is I not equal to I3?
It is.
I naught is not equal to I3 because I3 goes through there. I naught and I5 are equal to each other. Yeah. The water going through there is the same water going through there, and since it did split, it would not be the same, but it did merge back together.
It's
So-
different when it splits, but anytime else it's the same.
Yeah.
So these two add together to be I5 then?
Yes.
Got it. Thank you.
On this one, like, how would I know what that means? What you're asking for?
That's C capacitance.
Okay.
Also, you could say, I think it is a valid question to go, what do you mean by C?
Yeah.
And I would go,
Yeah.
the capacitance of the capacitor.
Okay. And then on this one, is this assuming an electric field that you're assuming that it's positive at that point, -2, because it's the tiny positive discharge?
No, I'm assuming, no, there's no assumptions for that part at all. It's got to be because you've got an electric field from a negative charge and an electric field from a positive charge. How do those vectors add up?
But the
There is no positive test charge at
Are you
that
saying
point.
it's particle? Doesn't have a charge? A negative 2.
I'm just looking for the
Yeah.
electric field at that point.
a negative-
There's nothing there.
Okay. That's
There's nothing, and now if a charge was
Okay,
there,
Okay.
I wouldn't be looking for an E field, I'd be looking for a force.
Whereas, and you would tell us the
I'd have to give you,
positive and negative.
yeah, I'd give you, yeah.
Okay. And so, yeah, so that's just the electric field, and you know that it's pointing based on the direction that an electric field points away from or to a positive or negative. Okay.
Yeah, it's all on logic now. Yes,
For this one, with the VA, you drew a VB just so you could do the high-low?
yes.
Okay,
Yes.
you chose to go this way because it was...
It's the easiest way to get to it.
Can you just explain that one more time? Why you step up? Like, can you
Well,
explain
I
it again?
stepped up because the current is going like that. So I'm going against the current.
Yeah.
So when you're moving from there to there against the current, your change in potential is positive IR.
That's going negative side.
Yeah, if you're going from there to there, it would be negative IR.
Okay. So the positive and negative.
It all depends, it's direction dependent.
So
Or against the current or with.
this came from...
Yeah. So that's the potential of where you started. That's the change in potential by going across the resistor. That's the potential at that point.
Okay, can you kind of start it
So the V0 is there.
in? Okay.
The change in V is the I naught R, and then the VB is where you end up, or the sum.
Okay. I'll have to look at some more. Thank you.
So Carla overheard the answer to my question, but why did you use I1 instead of I12? Like, why?
Well, what I did now, to what that particular step, what I'm doing is I'm finding VA.
Okay.
At this particular point, I've discovered what I12 is. I1 is equal to I2, which is equal to I12.
Oh, okay.
And I'm stepping down from V, so that potential is V minus
Okay.
I1R1.
Okay. That makes.
Mhm.
I'll put down. Thank you.
Next.
On the summer test, when it's an electron, and since F equals a little QE,
Yeah.
Would your charge end up being negative because it is an electron?
Well, what you would do is that the Q that you would get would be the magnitude, and then you know it's an electron, so you slap a negative sign.
Okay,
in
but
front.
you would want the negative. That's all I need to know.
Yeah.
Thank you.
On this last one, could you add a capacitor?
To this? No.
Okay, so we're gonna have an appetizer that's either gonna be something like this, or you said RC.
Like a motion. RC
Okay.
circuit or a motion, particle in a motion under the influence of an electric field.
Okay. And then these are definite, and that it's gonna be something about a capacitor, right?
Something. Can't tell you. Won't tell you.
Haven't made it.
Haven't made it.
Okay, can you just explain like the theory, not the non-math-based answer for what we did here, just so I can just have
The non-math, we used Ohm's law a lot.
yeah.
We used vector addition a lot.
Well, no, so like for these last two problems, like, so this V at this point, is that the voltage at that point?
That's the potential at that point.
Okay.
Yes.
And when you say potential, you mean like when I say voltage? Like,
Yeah,
Okay.
the
And
voltage.
and because voltage is inherently like potential. Okay.
Yep.
All right, okay. Cool. So the voltage at this point, which should be the same at this point,
Yes.
up until a resistor, right?
Yes.
The resistor changes it to something, right? Okay. The thing is that you have a three letter equation, like I don't factor equation, but you have a current, you have voltage, and you have resistance.
Yes.
We have the resistance, but we don't have the current, and we want to find the voltage.
Yeah.
Okay, so what did we do here to allow us to get the current there?
What I needed to do from here is, initially, I didn't know a lot of things.
Okay.
So I didn't know the current going through here. In order to figure out the current going through here, I had to know the potential there. And when I realized that I needed the potential there, I could get that easy. I step up from 0.
Okay, so you know the voltage here. Okay, and so if you know the voltage and you know the resistance.
And I know the total current, I can get the potential at that point.
Oh, okay. So, how did you get the total current there?
Total current there is the voltage of the battery divided by REQ.
Oh.
Remember what I said, the first thing you do out of the gate, give me REQ, give me I0.
Okay.
You got those two things, you can do a lot with it.
So, I'm sorry, like basically my main problem isn't the math, it's just understanding the conceptual stuff. So I'm sorry if this stuff sounds dumb, but like, why is the current here and here different? But the current...
Paperback. I'm just watching what you're doing.
Uh-oh.
You can.
Oh,
Watch
sorry.
it here because I can't see a thing.
The current,
Oh, okay.
the current there is the same as the current here running through. The current running through this line and the current running through that line are both different to the current running here. But the current, think of this like a stream.
Oh, okay. So it's connected here. So
Yeah.
okay.
So the stream comes down, it gets pumped up, it hits this, and then it forks. Goes down one waterfall, goes down another waterfall, and then they recombine.
Okay.
So the current going through R5 is the same as the current there, which is the same as the current going through the whole circuit.
Okay. So the difference here is that the current changes when it splits, and then when it comes back together,
Yes.
it's the same again.
Yes.
Okay. So we have a resistor here, we have the current, and so then so we find the voltage there. Is that what we find?
That's what we're gonna find. We're gonna find the voltage at that point.
Okay, yeah. And then by doing that, how does that allow us to find VA?
It makes it a known, now that VB is a known quantity, gets me closer.
Okay.
Now I can figure out I12 because I know high, low, total resistance.
Okay.
I is now can be a known quantity.
Okay. So you have the difference between the two voltages. And
Between the two resistors.
Okay.
So could you see where your V drawn? Could you use that as your V high and VA as your V low?
Yes, but the problem is, in the equation V high minus V low divided by R is equal to I1. At this particular moment, you don't know I1, you don't know VA, one equation, two unknowns, you can't use it. So you're gonna have to figure out I1. Well, how do I get I1? you're going to have to figure out VB because V minus VB divided by R12 is I1. Well, how do I get VB? Oh, I can deal with that. I can step up from 0. Now that you've stepped up from... We wrote it down.
So it's not the 100.
No. It's 0 plus I naught R5.
Okay.
That's it.
Okay. That makes sense. So you're finding a high and a low